Hello and welcome to Australia in Space TV. My name's Chris Cubbage. I'm the editor with the Australia in Space magazine. Today we're joined by Dr. Butler Hine, who's the HelioSwarm project manager with NASA's Ames Research Center. And Butler, thank you very much for joining us.
Thank you. Very happy to be here.
Wonderful. We're going to be talking about HelioSwarm project. This is a sort of hub satellite with 8 drones that go out, or drone satellites that go out around the sun. It's a fascinating project, but it obviously has a lot to relations here in terms of what we can do with swarms as well, and machine-to-machine communication, as well as the science. You're the project manager. Maybe just introduce us to your role and the project itself. And we're going to be seeing you in Perth next month, the 23rd to 24th of October, for the Indo-Pacific Space and Earth Conference. And again, this is very much related when we talk about the sun and what you are actually doing. So introduce us to the HelioSwarm project.
Sure, happy to. So I'm what NASA calls a flight project manager. So I'm the person who ensures that the whole thing comes together and works. We have a principal investigator who is the lead scientist. That's Dr. Harlan Spence at University of New Hampshire. And then I manage the whole project to ensure that the science gets accomplished. So that's my role. I'm actually a scientist as well, but I took a kind of a side path where I'm an astronomer, and I got interested in instrument development, and that led me into spacecraft design, and then I fell in love with actually designing missions and making them happen. So I've pursued that path in my career. So HelioSwarm is, as you said, it's a mission that's designed to investigate the heliophysics environment. The sun is the energy source for all of that, and as the plasma environment is affected by the sun, and you have kind of turbulent processes that transfer energy among all the length and time scales. It's a hard to understand process, and so a lot of the missions to date have been either single spacecraft or at most 4 spacecraft that try to understand what's happening in that turbulent environment. HelioSwarm is a different type of mission. We have 9 spacecraft that fly together. One is the central hub that we talk to from the Earth. And then the 8 SmallSats fly around the central hub, and they're designed to make science measurements of different 3D configurations. So they make measurements on different size scales simultaneously to try to understand the turbulent processes that are involved. It's an interesting technical mission because it's a true swarm, meaning we talk to the whole thing as a unit rather than talking individually to one spacecraft at a time. And the swarm coordinates among themselves for how to accomplish the mission. So it's both an intriguing science mission, but it's also demonstrating technology that originally came from terrestrial applications. There are swarm applications on the Earth, and what we've done is take that technology, apply it to a difficult space problem, and then obviously we'll have a feedback of that technology back into terrestrial applications.
Well, as I said at the pre-interview, I don't know where to start on this. As you say, it's the science and the technology aside. I might focus on the technology. I think the science will explain itself with the findings. One question I had in mind of why the 8 and that 3D model, how much variance do you anticipate to see if you haven't seen it before, and sort of what new science might come out of this, or new understanding around the sun and the sort of the plasma rays that come out. But maybe just focus on the swarming side of this. Is there new technology? Are you applying current technology as to this, or do you find that you are sort of creating new technologies that we could potentially apply here back on Earth, in particularly on swarming and machine-to-machine communications and coordination?
It's both. We do take advantage of technology developed on the Earth to enable this mission, but then what we find from the mission, especially the technology aspects, we do flow back or will flow back into terrestrial applications. So one of the things that's a key technical characteristic of a swarm is how communications happens, and also how the swarm control happens. It's very different. In a traditional constellation mission, you have the Earth talking to each spacecraft individually, and so all of the coordination happens on the Earth, and it's the individual commanding of the spacecraft that achieve the function that they're trying to achieve. In a swarm, as opposed to a constellation, you talk to the swarm as a single entity. So in our case, the central hub spacecraft is a much larger spacecraft. It's on the order of 1,000 kilograms. Right. And then each of the 8 node spacecraft that fly around it are about 100 kilograms each. So the hub is the one that they all attach to when it's launched, and the hub carries them all swinging around the moon, and then it swings us into our science orbit, which is a very high Earth orbit. And then the 8 individual nodes deploy. So in pairs, they will separate from the hub in pairs and go into the trajectories that they need to maintain. And the reason we have 8 is because we're trying to understand the 3D structure of the turbulence. And so at the heart of it, we look at large scales of polyhedra, and then also at the same time, we're looking at smaller scales of polyhedra. And it takes a minimum of 6 to do what we need to do to make the science measurements. And then we carry 8 so that we have redundancy in case 1 or 2 of the nodes have problems or fail. We can still get our core science with a minimum of 6 of the nodes flying around the hub. So what's challenging about this is if you look at swarms on the Earth, such as quadcopters, there's a lot of technology development around quadcopters on the Earth and how they can cooperate with each other to make coordinated measurements. But on the Earth, the difficulty with a swarm is how it handles things like terrain and wind. So if you have a high wind condition, then sometimes quadcopters are not powerful enough to overcome the wind, and so they might have to stop operating, or they might have to go into an extreme physical configuration in order to compensate for the way the wind blows. They also have to worry about colliding with things on the Earth, and so if they're flying low, they have to worry about hitting trees or buildings or people, and so that's what makes swarms challenging on the Earth. If you go to the underwater world, there are also swarms that are underwater vehicles. There, the environment is even more difficult because the equivalent of the wind underwater can be very strong currents, and it takes a lot to overcome those strong currents at times. Plus, the terrain is hard to navigate around because you can't see very well. So that's why you use acoustics to see the underwater environment. Well, in space, the problem is slightly different. For one thing, we don't have to worry about colliding with anything because we're out there by ourselves.
Yes.
The main thing we have to worry about is colliding with ourselves. So we want to make sure we control ourselves so that we never collide from one node to another. But the challenge is when you're orbiting a body, it's not obvious how you move. If you're orbiting the Earth or orbiting the Moon or any celestial body, and you want to go in a certain direction, you have to actually fire thrusters in an orthogonal direction in order to go. So orbital mechanics or trajectory is a very dominant force. It's even stronger than what you see underwater. And so that's the real challenge, is how we design the swarms trajectories so that the nodes achieve the configurations they need to achieve, while doing the maneuvers that they need to do to maintain the configuration. So at heart, the technology we're using is current state-of-the-art technology in terms of spacecraft. What's new about it is how you manage a swarm and how you get it to fly the trajectory it needs to fly to achieve the science. And once we develop and deploy the ability to do that type of control, that will directly feed back to terrestrial applications where you have challenging cases like that, where it's difficult for the swarm to maneuver.
And is it autonomous? Is it learning itself as it's doing? I mean, obviously, the communications, you can't sort of send sort of instructions to the hub, and obviously there's going to be a bit of a delay. But I take it this is autonomous learning, and each swarm member is doing their own thing, but feeding it back to the hub. How does it actually work, sort of individually for each of these sub-satellites?
There is a level of autonomy, but it's not the type that you're thinking of. In this case, each spacecraft, each of the 9 spacecraft takes care of itself. So each spacecraft knows how to orient itself properly to communicate. It knows how to orient itself to achieve the science measurements, to point the instruments in the direction they need to go. Each spacecraft knows how to keep its solar arrays pointed at the sun. So in that case, all the spacecraft are autonomous in the sense that they are taking care of themselves. However, the swarm, as it works as an entity, it does receive instructions from the ground. For instance, the trajectories are very difficult when you're orbiting a celestial body. It's very difficult with current state-of-the-art for a spacecraft to know where it is in space. It can usually tell what attitude it has because it can see the stars, it can see the sun, it can tell what attitude it has, but it is very difficult for a spacecraft to tell what trajectory it's on. That's something that is, to date, has always been provided from the ground. Now, we do have technology investment at NASA to enable spacecraft someday to be able to deduce their own trajectory. But right now, we don't have that capability to great extent. So in this case, our orbit is a 2-week orbit, and then every week it gets close to, the whole swarm gets closer to the Earth, and it talks to the Earth, and that's when we tell the swarm, here's where you are in space, and here's the maneuvers that you need to do individually to correct your motions to make sure that you can still do the science measurements. That's also the time that we download all the science data that the swarm has accumulated over that 2-week period. So I wouldn't call this an autonomous swarm. We're working towards that at NASA, but we don't quite have an autonomous swarm yet. We do have a mission up there right now that just launched from New Zealand, actually, about a month ago, called Starling. And it's for smaller spacecraft that are flying closer to the Earth. And it is actually investigating technology. It's not a science mission, it's a technology development mission. And there, that mission, which HelioSwarm is related to, is investigating how the swarm talks to itself, how the swarm communicates with the ground. And it's doing a lot more of the autonomy as a tech investigation that someday would apply to missions like HelioSwarm.
Well, I'll take it the other one, and you're scheduled for launch in 2026, I understand. Yeah, go.
It's 2029 now.
Oh,
We were selected. There were 2 missions selected at the same time, and then one was selected for the first launch opportunity, and the other one was 2 years later. So we're targeting 2029.
Oh, you got plenty of time up your sleeve. You have problems to solve before you do this. So obviously, this is a live project, and you've got an end goal, but you are yet to solve some problems before you go.
Yes, we do. A lot of the problems are around things like how do you build numerous spacecraft identically on a production line.
Right.
That's something that the Blue Canyon Technologies is the Node spacecraft provider, and that's something that they have pioneered, is the ability to build multiple spacecraft that are identical. We also have on the science side, each spacecraft carries 4 science instruments. Each spacecraft carries 3 science instruments, and then the hub has a 4th and a 5th science instrument because it's bigger. And so we have to do production line building of the science instruments so that they're all identical and can take the same science measurements. And then we are in this development phase we're in right now. We are investigating how to have the swarm achieve the trajectories that are needed to optimize the science that we're trying to achieve. Because turbulence is a problem we've had for hundreds of years. No one has solved it. But it's ubiquitous around the universe. We have turbulence everywhere, at stars, in galaxies, in black holes, and so understanding turbulence is a core science goal that we're addressing.
Well, you mentioned the Rocket Lab launch out of New Zealand. Is there other sort of programs and projects related to HelioSwarm other than that one as you move forward and trying to solve these problems? I take it you have other projects to try and solve some of these?
We do. There's technology demonstration going on all of the time at NASA. Starling is one that is a direct predecessor to us because we're hoping to use some of the technologies that come out of Starling. But some other missions that are happening are optical cross-link communications. So using lasers to communicate between spacecraft. We have actually in one of my previous missions, we demonstrated laser communications between the Earth and the Moon. But now we're also trying to demonstrate laser communications between 2 spacecraft. And that is a key enabler for swarm technology because large bandwidth communications between the swarm elements can enable a much greater type of autonomy than is possible when you have limited bandwidth. So communications is a big demonstration. In fact, at the end of HelioSwarm, when the science is all done, typically NASA assigns some time on missions that have completed successfully. We try to do technology demonstrations on those missions. And you see that now we have on Mars, the Mars rover is testing helicopter technology on Mars. It's not being used for a science purpose, but just purely to demonstrate the technology. And then in a later Mars mission, it will be used for a key science purpose. We have something similar on HelioSwarm where at the end of the mission, we're going to reconfigure the communications approach between the swarm elements. And so instead of each swarm node talking directly to the hub, we're going to deploy an ad hoc mesh network so that the communications can go between any elements of the swarm and can be relayed between swarm elements to other swarm elements. And doing that will greatly expand the physical extent that the swarm can achieve while staying in communication. So that's a key technology that we're planning to test on HelioSwarm later that's currently being tested on other technology missions now.
Amazing. I did see a release just the other day out of NASA in terms of the optical communications demonstration. I don't know if it was coming or just happened, but I know I saw it and it was up on our channels. But are you going to be in Perth, as I mentioned, for the Indo-Pacific Space and Earth Conference?
Yes.
And presenting on HelioSwarm? Is there any aspect in terms of when you do present publicly that you tend to focus on, or do you try to sort of encapsulate the whole project? Is there certain aspects that you try to send out in terms of your key message?
Well, what the conference has asked me to talk about is the HelioSwarm mission in its general objective in achieving the science, but really to focus on the swarm technology aspects of it. So how we're doing this mission using swarm technologies that have been developed on the Earth, and then what we're hoping to achieve with that, what's challenging about that. So that's mainly what I'll be focusing on, although all of this is done in the context of achieving this highly important science that we're trying to achieve. So that's always the context of what we're doing.
And just lastly, I suppose that there's a lot of applications for on Earth in terms of machines. You know, we think sort of you mentioned drones and the like, but also robots and robotics. and moving robots. Something that we'll be covering off in Perth is the cross-sector, the mining and the agriculture. So a swarm, in your mind, it could be a flying object, but also a sort of on-ground object as well.
Yes, there's currently in the terrestrial world. There's three classes of swarms. One is the flying swarm that we're familiar with. I mentioned the underwater swarms, but there are also surface swarms that are robotic systems that are designed to either cover a large ground and do a distributed sensor application, or mapping is a big application for these ground swarms. Communications relay is a very important technology for ground swarms, because when you're in the air, you often have longer line of sight with other aerial assets. But when you're on the ground, these mesh networks that I talked about are very important, because every element can't see the other elements. So sometimes you have to pass messages in a network fashion from one swarm to the other, from one element to the other, in order to get communications across the swarm. And then a big subset of land swarms is subsurface swarms, such as mining. Those have, I would say, particular challenges, because it's a difficult 3D environment. When you're in the air, you mainly have to worry about the ground. You don't want to crash into the ground. When you're underwater, you're often in a vast expanse, and once again, the main thing you worry about is getting deep enough to touch the ground. In a cave environment, you have terrain all around you, and so it's a very difficult mapping problem. It's a very difficult communications problem, and it's a difficult contact or collision avoidance problem. So the underground swarm is probably one of the most challenging environments.
Well, it comes to mind, our CSIRO came second in the DARPA subterranean contest recently. And lastly, is there a definition on swarm? Is it just two or more? Does it have to be three or more? What's the definition there?
Well, there's a bit of a nomenclature debate about that. What we use for space applications is, if you are talking to individual elements from the ground, that is considered a constellation. And a lot of our communication satellites are constellations. When you're talking to the swarm as a single entity, then that's considered a swarm rather than a constellation. So it's how you talk to it and how you command and get data from it that is the difference between a swarm and a distributed resource like a constellation. As far as the number, I would say if it's less than three, it can't be a swarm. But typically, swarm is a term applied to large numbers. In that context, HelioSwarm with only 8 members is actually a small swarm. Some of the later NASA missions that this technology will apply to, the numbers of elements get into the 1,000 range.
Yeah, I think it's important. It's a good takeaway. Otherwise, you've got clusters. Otherwise, I take it. But the terminology and the language around some of this technology is quite important to get as well. But Dr. Butler, Dr. Hind, I could literally talk to you all day, and we've hardly even touched on sort of the science aspect. For the audience, we'll have links in the show notes to a range of different aspects of this project. But otherwise, you can catch Butler in Perth on the 23rd to 24th of October at the Pan Pacific Hotel for the Indo-Pacific Space and Earth Conference. Butler, thank you so much for your time, and a pleasure, and enjoy the rest of your day there in California at the NASA Ames Research Center.
All right, thank you very much. I'm looking forward to coming out there and seeing everybody.
Wonderful. Thank you very much.